So I was told this was a TED-style talk. Let's see, it's not too close to that, but as close as we can. So I'll be talking about sustainable energy decisions. And the first thing that I'll talk about is really the graduate students and postdocs that I've worked with in the past, because they are the ones that have been helping spur all this line of research. And now highlighting the ones that are current students now at Stanford University. When we think about sustainability, the Brundtland Commission report comes to mind. This is an old definition from the 1987, thinking about meeting the needs of the present without compromising the ability to generations of the future to meet their own needs. This has been established through the UN reports and more recently thought about in terms of sustainable development goals. There are 17 of them, ranging from no poverty, zero hunger, good health and well-being, quality of education, gender equality, clean water and sanitation, affordable and clean energy, decent work and economic growth, industry, innovation and infrastructure, reducing inequalities, sustainable cities and communities, responsible consumption and production, climate action, life below water, life on land, peace, justice and strong institutions, and even more importantly, partnerships to achieve those goals. This is really in line with this new school of sustainability, and I tend to highlight over here the type of research that my group tends to pursue, which focus on affordable and clean energy at the center, but with ties on how to achieving the sustainable and clean energy when considering the impacts to health, how to reduce inequalities, how to produce sustainable goods and services through sustainable consumption and production, how to tackle climate mitigation and climate adaptation. And I highlight this goal 17 because without looking at these different facets through interdisciplinary approaches, solving these questions is virtually impossible. Climate change is here and now. What you see here in the animation that will start in a little bit are the temperature anomalies for different countries around the world. This is time-lapse, moving forward fairly slowly, but we'll get to 2017. And what you'll see all across these different regions is the temperature anomalies with increase in temperatures in particular, increasing all around. So something that may be thought of as impacts and temperature increases for the far future is just happening today, and we're already seeing several of the effects of doing so. Not only that, but we're running out of time to meet the 1.5 degrees C. This plot from the latest IPCC report shows the global warming relative to 1850 and 900 period. And what you see is that the most likely, those are scenarios, they are not projections, but all across the portfolio of scenarios that are illustrated here, C1 are the only ones that allow to achieve 1.5 degrees C. At the same time, a lot of those emissions come from the energy sector, I'll say the bulk of them. This plot shows the global energy consumption by source on the vertical axis from 1965 and up until today. And the key point is that 84% of the energy that we use and consume today is still fossil fuel based. And that's not necessarily a bad thing. It provides you a lot of quality of life, a lot of services. It has served us well, but it also has very large negative externalities that we need to account for. And there are two that my group focus on. So through the use of fossil energy, both for the electricity sector, industries and services, and for transportation, we have the problem of emitting greenhouse gases. Those have global dispersion, they will stay for a long time in the atmosphere, they are kind of like diamonds, they will be with us forever, which could be a good thing, but it's not in this case. But that's not the only problem. There is also the emissions of health-damaging air pollutants, such as CO2, NOx, and PM2.5. Those pollutants react in the atmosphere with ammonia, creating secondary PM2.5. And this is a very different type of pollution. If we stop emitting it today, the damages will go away. So it's very different from greenhouse gases. At the same time, if they are emitted in the middle of nowhere and no one is exposed, the damage is zero. If they are emitted in the middle of a very densely populated city, you'll have a large premature mortality. How large? When we look at the number of deaths by risk factor, we have different causes. Air pollution, and here it's both outdoor and indoor, accounts for 6.7 million premature deaths annually, coming third in terms of the risk factors. So how can we estimate the consequences of both greenhouse gas emissions and air pollutants? We can use integrated assessment models, and these models basically combine very detailed information on emission sources. In the case of criteria air pollutants, the emissions of VOCs, NOx, ammonia, SO2, and primary PM. And then they are combined with models that look at the chemistry and dispersion of pollutants in the atmosphere and the exposure to air pollution. So after a baseline run, if we want to do some attributional analysis, saying power plant A is worse than power plant B, what we can do is go specifically at the geolocation of that power plant, increase incrementally a ton of one specific pollutant, understand what happens in terms of the chemistry and dispersion in the atmosphere, and assess who is exposed to that air pollution through the increased concentration of PM2.5. Now, if we couple that information with census information about population, we can then assess the level of premature mortality in different locations. Let me illustrate what I mean. For example, we have looked at coal power plants and the amount of generation that they provided for a recent year, and we can compute the health damages incurred in $1 million from the emissions from these point sources. This begs the question, do we all breathe the same air? And the answer is we don't. So in this plot, I'm showing the premature mortality by race and income associated with power plant emissions. The vertical axis shows premature deaths per 100,000 people associated with electricity generation. The horizontal axis shows income for the households by group. And we see that households with higher income are located in places that have slightly cleaner air. So the premature mortality is a little bit lower than 5.3 premature deaths per 100,000 people. Now we can parse this out using the census information, also by race and ethnicity. And what you see here is that Black African American are facing higher exposures to air pollution at all income group levels, followed by a white non-Latino. There are many reasons for this, and we can expand on that. But what I want to talk about next is really thinking about, can we make better decisions when we take into account both climate change and air pollution damages? So we created a model, a capacity expansion model that has the characteristics of all power plants in the United States and their emissions and damages. And we ran two scenarios. In all these scenarios, the goal is to reduce CO2 emissions from the grid by 30%. But we can do so in different ways. We can retire coal power plants in the middle of the Midwest, or even some of the steel oil power plants in Texas. And so how can we go about those decisions? And we look at those decisions under two goals. The first goal is minimizing the costs of building new infrastructure and the costs of climate change. And in the second goal, minimizing not only the cost of building up stuff, the cost in terms of reducing damages from climate change, but also reducing health damages from air pollution. The constraint is binding, so if we want this model to reduce emissions of CO2 by 30%, that's what it's going to do, and we use a social cost of carbon to understand what are the annual benefits. And we see that the emissions across both scenarios are the same in terms of the reductions from CO2. And in both cases, we have co-benefits in terms of reducing air pollutants that cause premature mortality. But as you see, if we explicitly incorporate the damages from air pollution in our decision functions, the types of plants that will be retired and their location is going to change. And now we'll be retiring plants that are upstream from highly densely populated areas. And we have costs, of course, in building this whole new infrastructure. But what is the most interesting is that we're not pricing these damages currently in the market. And if we were to, we would have net benefits. This meaning that would actually be better off as a society if we were to internalize those damages, but they are simply not priced. And if they were, at least a part of this transition would make sense. There is a lot of uncertainty surrounding those figures, so we generally run more than one air quality model, and the results are robust all across. The work that I talked about up to now focused mostly on the United States, but our group is starting to have a lot of work related to India. We created a model also that accounts for the emissions of CO2 and criteria pollutants for the Indian power sector. And one of the key results that we published a couple of weeks ago in Science as a research article is really showing that even if you have very high carbon prices, the emissions reductions in the power sector are going to be virtually zero. And the reason is you don't have other types of plants in the system right now, in a system that is so dominated by coal, that you can use to decrease those emissions. So though in the long term, through new investments in infrastructure, we can get there, in the short term, the carbon price will be something that is very costly and achieving a very limited impact. We also found that if India were to move their electric power operations to something more similar to what we have in the United States in terms of having a coordinated dispatch that is regionally organized rather than just state level, would also not lead to dramatic reductions. There is one other thing that could have impact, not on CO2 emissions, but on premature mortality. Coal power plants in India still don't use air pollution control technologies. We do here in the United States. And so the premature mortality in India is immense. We tested the costs and effectiveness of reducing those emissions, and we find this would be a really cheap policy to implement, and it will save a lot of lives. Our energy systems are more and more interconnected, so the decisions that we do in the power sector affect other things. For example, as we move towards decarbonization, one of the key questions is, should we electrify everything, namely the transportation sector? So are we better off by having an electric vehicle instead of an hybrid gasoline car everywhere? And should we just move in that direction? And the answer is that it depends. It depends on the electricity with which you charge your vehicle. So our group has looked at computing life cycle emissions for different types of vehicular technologies and coupling that with tools that we've developed that track the emissions of CO2 and criteria pollutants for every single balancing area across the United States. We also account for the fact that these technologies perform differently, meaning the energy consumption of the vehicle under different temperature profiles for an hybrid gasoline vehicle versus battery electric vehicle is very different. If you drive in highway-style driving versus city driving, once again, the energy consumption of the vehicle is also very different. And so you may be surprised to find that when we compare BEVs, battery electric vehicles, to hybrid gasoline vehicles on the right, and when we include the full life cycle, the results may not be what we expect. So we include the vehicle manufacturing emissions, battery emissions, the electricity used in this figure showing for the average grid in the United States, and gasoline use emissions. And we also run a bunch of sensitivity analysis looking for more close to real world conditions for driving, the ranges of temperatures and type of driving across counties, where the batteries are manufactured, and the annual distance driven. And what we see is that for some, under these very simple assumptions, the Tesla Model S, for example, has higher emissions than an hybrid gasoline vehicle, and that the emissions are not that different across different types of vehicles. But now here's the catch. This is on a very aggregate level, and I would argue we need to call for more regionally tailored policies because the results are very different across the country. Here we're comparing the emissions from a Nissan Leaf and the Toyota Prius, the Chevy Volt and the Prius, and Tesla and the Prius. So at the top, you have battery electric vehicles, and then on the side, you have hybrid gasoline vehicles. And we see that where we're located right now, we should electrify. It's a no-brainer if the goal is to reduce emissions. But in parts of the country, if we were to transition to vehicle electrification without decarbonizing the grid, we'd actually be increasing emissions rather than decreasing. Things will change as we change the grid and as we decarbonize in the Midwest, for example. But right now, and with reasonable data from when the vehicles will be charged, those are the findings. And so we've tried to provide tools that can inform decision makers. For example, by understanding how much does the grid need to decarbonize in these different locations for electrification to make sense. In all the regions that you see that are transparent or white over here, the critical emissions factors have already been achieved, meaning we should electrify. Across all the rest of the country, we really still need to decarbonize the grid in order to get there. So in terms of key takeaway messages from this work, it's really in terms of environmental justice is something that is tremendously important as we think about this energy transition. The consequences may not be obvious, but one of the really good news is that we do have data that allows us to take a serious look and quantify what are the outcomes from different decisions. In the context of the electricity sector in the United States, as it stands today, exposures are the highest for Black African American people, followed by white non-Latino, and those differences persist even across different levels of income. When we think about decisions for decarbonization, it's a mistake to ignore that there are other externalities and environmental damages that need to be considered. And specifically the damages to health that are associated with air pollution. And so bringing those two together can actually be beneficial from a society point of view. We may find it surprising that electrifying everything everywhere is not yet the best decision, and that we may need a combination of technologies and portfolios to have an energy transition that indeed reduces the emissions from day one. And finally, there may be some places, for example, what we found in India, where it's an imperative to decarbonize the grid before we do decide to foster electrification. Otherwise, we're going to be actually worse off rather than better off. Thank you.